Alright, got that going.
6 times 3 is 18, correct? Yes. Okay, I like it so weird. So it's really weird.
Except,
But we have, but plus 1. But mine, right? No, it's negative, so we add 1.
negative charge, yeah, extra. Blame Ben Franklin. All his fault. Riley, yours looks good. Why don't you try assign formal charges to all the atoms?
I need my notes. Didn't take notes on this.
So formal charge, remember, is how many electrons does it have,
Okay, yeah, and how many
and
does it want?
how many does it have on its neutral on the periodic table? Right,
Just in the game list, so, well, it doesn't really matter.
remember, we're talking about ohms, so all the ones in bonds, it kind of owns half of those.
It's 5, so.
So if it's got 4 and it started with 5, it's missing an electron, right?
Do you do
Correct.
what it wants minus what it has?
What it has on the periodic table
Yeah.
minus how many it owns now.
Is there a sign for neutral? Or do you just leave it like?
You can just do like a superscript 0, but not typically.
Okay. That's fine. That's how I did it. I just counted 1, 2, 3, 4, 5, 6, 7. So that this one's negative, this one's negative. But then one of the negative positives, that's fine. Oh, but I figured the way that this would actually look is to make it like all happy, the price, right? So like, yeah, like, yeah, sure. But you're gonna get, I don't care. Looks better, it's corrector.
Oh, that's
Corrector, what's the nitrogen? Is it happy?
so there,
No.
we're gonna talk more about.
No, it's not. No, it's right here. But then this one and this one. For the overall cancel out, or do you want it like? Posted next to that, that's what I did.
Either that or some of that, you can even just put it, see if this will work now. There we go. So we all came up with the same structure. Now, if we're trying to figure out formal charges, we all figured out nitrogen's a +1, so you can do it just like that if you want. We wouldn't necessarily. I guess in OChem we do frequently put the charge when we start drawing these larger structures. When I'm first teaching formal charge, I usually do it this way, make it really clear which one I'm talking about without clouding it up and counting it as an electron. And again, you don't necessarily need to draw the lone pairs with the little loop. But on a whiteboard, it's really easy to miss the little dots if you're not really careful. So drawing it just without that, but just to re-emphasize where all the electrons are, like standing where you are, Riley, looking at yours,
Yeah, you can't see.
like you can see them okay, but I can't. Cause they're pretty tiny dots, right?
Right.
So this is just a one way to be fast about it, while but still being like really clear, hey, there's a pair of electrons taking up space there.
Yeah,
So, and we figured out this oxygen's gonna be a 0 as well, right? It owns 6 and it has 6 on the periodic table. To put it back in the terms that we used at the end of class on Tuesday, this oxygen has 2 bonds. If you have oxygen with a full valence and 2 bonds, it's neutral. If you have oxygen with a full valence and only 1 bond, it's got an extra electron. So that gives it a -1 charge. So oxygen with 1 bond is always going to be negative in this class. Not always, but usually going to be negative. Nitrogen with 4 bonds is going to be positive. And so both of these are going to be -1. So if we did our formal charges properly, they should sum up. If you add up all the formal charges, they should add up to the charge of the molecule. Which they do, right? Let's do one more. Or do we need to get into that? Maybe think about that. All right, we have more examples of formal charge here in a minute. But so here was where we ended the other day, right? When carbon has 4 bonds, it's neutral and stable. Our rules for stability, you guys can sit down wherever you, I think.
okay.
Give me a second, and then you're gonna immediately want to stand back. When carbon has 4 bonds, it's neutral. And we're gonna go over the rules for stability, but the most important thing for stability is that it has a full valence for all of these. When something has a full valence is when it's is the most important factor for it being stable. Something having a formal charge, the next thing we want is for the formal charge to be as close to 0 as possible. Right, so when we were looking at our nitrate, there's a lot of molecule or a lot of atoms that have formal charges here, right? Got a +1, -1, -1, and then a 0 there. None of those are really like the most stable they could be, because when the formal charge is closer to 0, that's usually best. However, in this case, this is the only way we can make it so that everything has a full valence, and that's what's most important, is having a full valence. So, and actually, I guess this goes into our rules for Lewis dot structures in general. The most important thing is using the right number of electrons, because we can't make matter out of nothing. Turns out the universe does that sometimes on its own, but that's more of a theoretical physics thing than it is a chemistry thing at this point. So then the next most important thing is, did you fill valences? Sometimes you can't fill all the valences based on the number of electrons. So sometimes you get stuck at number 1. You can use the right number of electrons, but you can't fill the valences. If you can do both of these and you still have a couple options, the next most important thing is formal charges close to 0. Right, we'll start splitting hairs with that even too. Is it more important if the oxygen has a formal charge close to 0, or if the carbon has a formal charge? Like, we'll start getting into some of the specifics there as well. But these are the 3 criteria for your Lewis dot structures in that order. So just to do one more example. CH3, CH2, the positive charge. So the carbon that's neutral, we know how many bonds that's gonna have, right? Instead of counting electrons, we can just say, well, it's a carbon that's neutral, it's gotta have 4 bonds.
Yeah.
And we know that the other carbon has a positive charge. We're gonna leave that alone for a second. But we know it's got 2 hydrogens attached to it as well. How many total valence electrons do we have to work with this molecule?
Wait. Like both carbons?
Yeah, the whole thing.
Oh.
We're just gonna add all of them.
8.
So 8 from the carbons plus another 5 from the hydrogens, right? And it's got an overall positive charge.
So take away 1.
So we're gonna be missing 1 electron because of the positive charge. We're pretty sure it's gotta be arranged something like this. Do we have any more electrons to give? 2, 4, 6, 8, 10, 12. So we're out of electrons. So this is one of those examples where we get stuck at number 1. We can use the right number of electrons, but we can't fill all the valences. This carbon is stuck with an incomplete valence. And just because we're going to talk more about different types of structures today, different ways to draw them. This is our complete structure that we first introduced the other day, showed everything, right? This is the way to make sure that you know everything that's going on. You're being really explicit with everything that's going on. This is the fast way to do it though. So this is a little bit different than just writing the molecular formula, because we actually show some structure despite the fact we just wrote it like formula. We didn't write it as C2H5 with a plus charge, right? That's the molecular formula. This is called the condensed structural form. And it's kind of a holdover from back in the days before you could really easily do skeletal structures. Because if you're trying to set type in an old school printing press, it was not easy to actually draw even a complete structure like this. And so you saw a lot of condensed structures just because you could type it or set it in type when you were making your printing press.
That's what?
Condensed structural. And this is the complete structural form or a complete structure. The skeletal for this one looks really weird. We don't usually draw skeletal structures for molecules this small because it looks more confusing.
Yeah.
But that's technically what the skeletal structure would look like here.
So you assume a carbon at each point, there's hydrogen coming off each one.
There's enough hydrogens to fill the carbon's valence unless it has a charge.
Okay.
So in this case, because this carbon has a plus charge, we know it's only got 3 bonds. 1 to the other carbon, 2 to hydrogens. And then it's got a positive charge. So it's got an incomplete valence. So here's another good, I think I can say this is a universal rule. I don't even think I have to put caveats on it. A carbocation will always have an incomplete valence. So I don't even like saying that word. It makes me uncomfortable to say always. Because I'm sure there's an exception out there. for now, we can say, if you see a carbocation, it's gonna have an incomplete valence. What about if it was a carbanion? It was CH3, CH2 with a negative charge.
Would you do the double bond or an extra hydrogen?
Let's
We
work
wouldn't
it
have
through.
anything, right?
We wouldn't have enough hydrogens, because it's still CH3, CH2 with a negative. This is all that changes though. We have an extra electron instead of a missing electron, so instead of 12 electrons. We have 14 electrons. So now what is that complete structure gonna look like? If we've got one extra pair. The way it was drawn here, this was only 12 electrons, right? We've got an extra pair of electrons now.
So they
Be a lone pair. And now this carbon's got a negative charge to it because it's got 5 electrons owned. Instead of just 4, instead of 3 that it had when it was a plus charge.
So would you say what opposite of
Carbanion.
Oh, that's right.
So anion
And
is it stands for a negative ion. And you just put carbon from it.
so it's going to have a low pair.
Correct. And so we can
Always.
I think I can say always for that one too. I can't think of a case when you've got a carbanion ion. That it doesn't have a negative, and I think you can say that for anything in row 2 periodic table. If it's got a negative charge, it's got a lone pair.
Carbon would never take on 5 bonds, right?
Correct.
It would only ever go to 4.
Only ever go to 4. And same with, again, everything in row 2. And that's a hard stop.
Okay.
You can't break the octet rule until you get a d orbital involved, and nothing in row 2 has a d orbital that's really close to the same energy.
Okay.
Alright, so let's do a couple more practice for formal charge. You can use the whiteboards if you want, or you can come up here and use the smart board if you want. Or your own. So-
Go for it. Can we use that one? No. Oh, okay. Navigating that. Wait, but you have the periodic table. I didn't practice memorizing one.
You need 2 screens here, so I can put a periodic table on one
Yeah,
side
right.
and
I
Slides
have
will
my
be there.
screensaver, but it's not very.
yeah.
You should just print out a big one. We have a big one somewhere that was in the G lab. Where did that go?
They don't want us to put periodic tables in the classrooms
right.
because they're not technically allowed to be designated. This is not technically allowed to be called the chemistry classroom.
A periodic table, that's just the elements that make everything.
You're preaching to the choir here. Well, and we have maps of Latin America in the Spanish in classrooms where they teach Spanish, and we have topographic maps where we teach geology. But for whatever reason, they fought me on putting the periodic tables back up, so that's why I just print them out for you. If you need a new printed copy, Taylor, just let me know.
I have a million somewhere, I just need to find stuff.
What's up there, the aluminum is the trickiest one, actually. Everything else we've actually seen examples of,
Where
right?
we go from.
I don't know, we should find it for the aluminum. Yeah, that's correct.
Okay,
It's got a full valence, it's got 8 electrons around it, it owns 4 of them, and it's got 3 on the periodic table. So. -1 hydrogens are all neutral. That also actually helps make my point. The point I'm about to make. I don't like to remember formal charge as a formula, like this minus that. I always just look at it, how many electrons does it have now versus when it was neutral? If it's got an extra electron, it's gonna have a negative charge. If it's missing electrons, then it's gonna have a positive charge. Right, so for oxygen, we're always comparing it to 6, because
yeah,
that's what's on the periodic table, right? So if we're comparing it to 6, it now has 5 that it owns. So that gives it a +1 charge. And same down here. In both cases, the oxygen looks different. The structure looks different, but at the same time, it's an oxygen with 1 lone pair and 3 bonds.
yeah,
If it's got 1 lone pair and 3 bonds, it's always gonna be +1. So this goes back to all you really need to do is count the bonds and then assume the lone pairs. In OChem. So you see an oxygen with 3 bonds, it's +1. You see an oxygen with 1 bond, it's -1. You see an oxygen with 2 bonds, it's neutral. And the way to make sense of that is if it's got an extra bond, it's sharing more than it wants to. If it's sharing more than it wants to, it's gonna have a plus charge, right? So if you always know the number for when it's neutral, it's easy to figure out the charge from that. And again, hydrogen with 1 bond, always gonna be neutral. You will never see a hydrogen with a charge unless it's all by itself. Hydrogen all by itself can either be H plus, in which case it has no electrons, right? We've learned that from acid-base chemistry in Gen Chem. Or you can have hydrogen with a lone pair because it needs 2 electrons to fill its valence, right? So if you have hydrogen with a lone pair, it's gonna have a -1 charge. So we call that a hydride. Turns out hydrides are not very stable on their own. They'll pretty much always find something else to glom, and protons for that matter. They pretty much always find something to glom onto. So this molecule here, AlH4 with a negative charge, is called a hydride source because the hydrogens are actually more electronegative than the aluminum is. So basically, instead of this acting like a weak acid where it gives away an H plus, it'll actually give away a hydride instead. And it turns out most of OChem, most of chemistry period, unless we get involved in nuclear chemistry or physics, most of chemistry is just chasing the charges. The only fundamental force we really spend any time with is electromagnetic force. So we're always looking for charges, charge density and electron density. So anytime we start showing mechanisms for how a reaction happens, it's always going to be following the electrons. That's why we're spending so much time talking about charges right now. It's because charges form the basis for all of the reactions we're going to study.
And you said the H with the low pair is fine.
The H with the lone pair is hydride. Just remember, I meant it had a negative charge, like fluoride, etc. So hydride versus, we just call this a hydrogen ion or a proton. And if it was hydrogen that was neutral all by itself, it's actually just got one electron then, right? So it doesn't have a complete valence. So we would just call that a hydrogen atom. Hydrogen's kind of tricky because it has 3 different structures that it can have pretty easily. So that'll become second nature because we're going to deal with hydrogen almost as much as we deal with carbon in this class. How about C? The carbons have a charge?
No.
Both have 4 bonds, right? So they're neutral. Hydrogens are all good too. The nitrogen,
-1.
-1. When it's neutral, it's got 3 bonds, right? So it's got 1 bond less than normal, so it has extra electrons. So it's a -1. And then we already did one example of a carbanion. This is going to be just like the one we did on the previous slide, right? Carbon's got 5 electrons, or it's got 3 bonds with a lone pair, which means the carbon is a -1 charge. All right. We're going to also define some terms here. We're going to switch from talking about electrons for a minute and talk about isomers. In the, I don't know, 2 weeks that you studied OChem and Gen Chem, we probably talked about isomers a fair bit, but just to reiterate, an isomer means that you've got the same formula, but not the same bonds. Or at least that's what a constitutional isomer is. We're going to talk about stereoisomers, optical isomers a little bit. But basically, it means the same atoms, but a different arrangement in space. Right, so for both of these, they're both C2H6O.
Yeah.
But one is an ether, and one is drinking alcohol. And the boiling points are way different too. If you've ever gotten those, they use dimethyl, you can buy dimethyl ether. It's not the kind of ether that knocks you out, that's diethyl ether. Dimethyl ether boils at -22 Celsius, so pretty cold. What's that, a little bit below 0 Fahrenheit?
So how do you, like, what form is it in the diet?
It's in a pressurized can. So it's, if you've ever, they sell these kits for freezing warts.
Oh.
So if you go to the doctor and freeze off a wart, they use liquid nitrogen, right? Because they have a tank of liquid nitrogen and they won't sell you that at a pharmacy. But at the pharmacy, they'll sell you a pressurized can with dimethyl ether in it, and you basically spray it onto your wart and it freezes it because it boils off at -23 Celsius. Obviously very different properties between the two, right? Despite having the same formula. And so this is one of the reasons why we have these structural formulas, either the condensed structural or skeletal structures or complete structures, to show what we're talking about, because this is no longer a good enough way of describing this molecule, because this can describe a number of different molecules.
Yeah.
So, and we didn't really, when you first learned nomenclature in Gen Chem, we didn't have to worry about this too much because we basically just used structure, or we just used molecular formulas. We just basically ignored the fact that these exist. Now, it's not good enough, and so our rules for nomenclature in this class are that when you give something a name, it has to be unambiguous. There should be no way that somebody can misinterpret your name and get the wrong structure, as long as they know the rules too. Right, so this is ambiguous. C2H6O is ambiguous. CH3OCH3 versus CH3CH2OH. Those are both unambiguous. That part of the reason we use the condensed structure is so that we can differentiate between the isomers. One of the first things that you're going to have to learn how to do in this class, one of the things that's on the midterm is going to be, here's a molecular formula that has multiple stable isomers. How many isomers can you draw? And it's always going to come back to these rules. Make sure your carbons have 4 bonds. Make sure your nitrogens have 3. Make sure your oxygens have 2. Make sure your hydrogens and your halogens have 1. And so it's a little bit like playing with Legos. How many ways can you arrange things so that all of these conditions are met? But we'll have lots more practice with that in the future. For now, let's try how many constitutional isomers can we draw. Let's do A for starters. Actually, I better put my water bottle. So continue on. You think you've got A. There's at least 2 for each of these.
Okay. There are more than 2.
Let's look at it. So seems like we have to start by putting our carbons in there, right? They're the ones that are going to go. They form what's called the backbone of the structure, or they call it the carbon skeleton. There's not really another way to arrange it other than 3 in a row. We only have 3 carbons. There's not really a different arrangement we could have. Each one of them needs to have 4 bonds, so we can fill in 4 bonds. And then we've got 7 hydrogens, so that's a total of, we need 8 things around the carbons. 7 of them are hydrogens, 1 of them is chlorine. So we could put chlorine here and add hydrogen to the rest of them. There's 1, meets all of our criteria. What's another way we could arrange it? So like right there.
I mean, I did the other side, but yeah, it was this one, as they move around.
So we're going to talk about what the orbitals actually look like in these bonds. But it turns out, remember that these carbons are all going to be tetrahedral, right? which means they're in three-dimensional space and they can rotate around. As long as you only have single bonds, they're free to rotate around however they want. So if I was gonna actually show this with a little bit more detail. It would look like this, right? So because these carbons are all tetrahedral. And if this bond can rotate, which sigma bonds can, and I'll explain why in a few minutes. Then that means that, stand on this side so I can use the correct hand. So if the chlorine is my pointer finger, and my thumb and my middle finger are two hydrogens, if it can rotate, there's nothing stopping it, the chlorine from being in any of these three positions.
Right.
So that means that all three of these are the same. Okay, and it also means the fact that this is a three-dimensional object means that putting the chlorine on the carbon that's on the far left, well, if I took this molecule up and I flipped it like a pancake, then the chlorine would be on the carbon that's on the far right. So both of those are going to be the same molecule. Either putting the chlorine here or putting the chlorine on this side are going to be the same molecule. That's our other isomer. Because no matter how we flip it around or rotate it, we can't change if it's attached to the middle carbon.
So is there two ways to draw this one or three ways then, because you could put the chlorine, like does the middle seat rotate enough that we wouldn't, like it would be drawing the same thing if you put the chlorine on top of it?
Or think of it like, again, pick it up and flip it like a pancake, then the chlorine sticks up instead of down. So yeah, so it doesn't matter if I draw the chlorine up or down, as long as we have chlorine attached at the end, we have chlorine attached in the middle.
Right.
But we can't switch it back and forth between the red and the green without breaking a bond. That's our definition of a constitutional isomer. Is if I wanted to switch from one of these to the other, I would have to break a bond to do it. How about C4H10? So the easiest one to do is usually just put all your carbons in a straight line, right?
Right.
And then see if you have enough hydrogens to go around. It's the red one, constitutional isomer.
Wait, well, no, because it's not like a branch, like for it to be a branch, it has to be in the middle.
Right, said that putting the chlorine sticking straight to the right or sticking down was the same because it can rotate, right? So same applies here. So these are the same molecule. But we did find out that you can't attach It doesn't matter which carbon on the end you attach chlorine to, it's the same molecule, right?
Right.
But what did make it a different molecule?
It was it.
Attaching it to the middle, so if we take one of our carbons. And attach it to the middle instead of attaching it to the end, then like you said, Taylor, we've made a branch. Instead of just rotating it around. Are there only two for this one? Doesn't matter if we stick the branch up or down. Same thing, right? And if we try to take this carbon and then make it another branch by putting it to the middle one, that's the same thing we just had, right? So. As long as there's only like two constitutional isomers, it's not that hard to find them. What about C5H10? Well, I'm gonna clear this so I have more room. Easiest is keep your carbon backbone straight. So start with that and then see what it looks like. So we can have 5 carbons in a row. Could we have 4 carbons in a row with a branch? Seems like that would make sense, right? See why we stopped drawing hydrogens.
Yeah.
What about 4 carbons in a row and putting the carbon on this one? That would be the same thing flipped, right? So we can have 5 carbons in a row. We can have 4 carbons in a row with carbon attached to the second carbon. What would that look like? That's exactly the right approach. 5 carbons in a row is the simplest. And then you start saying, okay, well, what it would look like, what would it look like if I had 4 carbons in a row and then I took my extra carbon and I attached it in different places? That's a different molecule for sure. But we have 1 more carbon left to go. So where would we put it?
Just make your chain bond. Well, no, that'd be the same.
But then that's the same as this one, then, right?
Another branch.
Like up here,
No, they want different. No, that's what I'm saying,
like that. Isn't that the same as this one?
so we should put it off of the carbon that's already. Yeah, I'm saying put it off of the carbon that's already branching.
Yeah, and this is where drawing all the bonds out. On the carbons, you know that all your carbons have to have 4 bonds, right? So draw all the bonds. So adding our last carbon to this one anywhere is gonna give us the purple one. Adding our last carbon here gives us the purple one.
Wait, how, oh, yeah,
Because then your longest continuous carbon chain is still 4, right? Adding our last carbon here is still gonna give us this one. Because it's, if I do that, that's still 1, 2, 3, 4 carbons in a row with a carbon sticking off the second one. What's the last place we haven't tried
all
it?
the others.
Now our longest continuous carbon chain is 3. And we have 2 branches.
Would putting it in like the hexagon shape be a different?
So it wouldn't be a hexagon in this case, it'd be C5. If it's C5, the pentagon.
Okay. But then you don't have enough for all the hydrogen.
Exactly. We took away a carbon hydrogen, 2 carbon hydrogen bonds in order to link 2 extra carbons to each other. So this would be C5H10. Because if you add enough hydrogens to fill all the carbons, that's only 10 hydrogens.
So there's only 3 ways.
There's only 3 for this one. But if you look at C6, it goes, so we went from, so C4H10, there was 2 isomers. C5H12, there were 3 isomers. C6H14, there's 1, 2, 3, 4, 5, 6. It starts growing exponentially. The more degrees of freedom you have, the more ways you have of arranging things, right? It's the definition of a geometric growth, right? Because as you start, you have more ways to arrange things as you get. It's, you know, if you think about dealing a hand of cards, if you have a deck that's only aces, 2s, and 3s, there's only so many hands you can have, right? But as soon as you add the 13 possible cards you can have in 4 different suits, you have, you know, billions of combinations. Alright, so in general, I don't think I really have you draw complete structures for anything with more than 5 carbons, other than maybe once on the midterm, just to show me you can do it. Once we get larger than that, we're gonna start sticking to skeletal structures or some combination of the 2, sometimes. And even just something as simple as adding the oxygen to someone we already had. There's 2 examples here. If we add 1 oxygen to it, that makes it really a lot more complicated too, right? Because we could put an OH in 2 different spots on the purple one. Right? We could switch one of these hydrogens for an OH, or switch one of these hydrogens for an OH. And then we could do the same thing here. We could put an OH on the end of the chain, OH on the middle of the chain. Or we could make it like this molecule where we put the oxygen in between 2 carbons. So by adding that oxygen in there, we all of a sudden have like 8 stereoisomers. We go from 2 isomers to 8 isomers. I believe 8. 1, 2, maybe 9. I would have to draw them out. I can't do it in my head.
Right.
Alright. So that's a skill we're gonna keep building on. It's one of those things, the more we practice, the easier it gets to see them. And especially once we get confident enough that we can do skeletal structures, it speeds things up a lot. And so if I actually was gonna do the C4H10O, I would do it. We can go a lot faster. Once you trust your ability to to get the formulas right from, or get the right number of hydrogens from your structure. And then we could have we had two straight chains, we could put. The oxygen in the middle, do. That. Maybe that's all of them. I think that's all, what did I come up with, 4, 5, 6, only 7. Not as bad as I thought. But, like, I can do that relatively quickly because I've spent a lot of time doing this, and it's one of those things, when you learn the rules, it starts getting faster and faster, and you get more and more confidence with it, so we'll just. It's sort of like. Doing the constitutional isomers is sort of like the conversions of this one, you know, how you had conversion word problems, like every single day we read through conversions until you couldn't see straight. We're gonna do the same thing with the constitutional isomers because it'll start becoming second nature the longer. All right, let's talk about Linus Pauling in the couple minutes we have left. We done? No, sorry, we haven't taken our break yet, have we? Let's take our break yet, and we'll talk about orbitals more in 10 minutes. Let's come back at 5 after.
Okay.
Just had a moment of panic where I totally lost track of what time this class is supposed to end.
I do that sometimes at Silks. I'll be like, there's no way we're done right now. And I'm like, oh wait, no, it's not 4 o'clock, it's 4:15.
Right. Were those dragonfly bagels today?
Yeah. Yeah. Have you been there?
I've not, I've had them here a few times. They're always sold out when I try to go to their location. Right, you know where Sedelis is? You probably don't know where Sedelis is, 'cause it's far. Go down Johnson, you know where the DMV is?
Yeah.
So it's across the street from the DMV, away from 50.
I've seen that place before.
So Dragonfly is right next to it, and then Sedelis is a brewery that we go to a lot because Chris Seidel, one of the owners, is a former student of ours.
Oh, cool.
He was, and he actually started, he was a student worker at Enrollment Services when my wife started working here. And they both worked enrolling people over in student services for a couple months before he transferred to Davis.
Sure, don't let me. They're safe for the thing. Just see how it's really nice. Just find the parking lot, it's not rough around left and left. What? Yeah, we're drinking, or no, what do you mean?
Go, actually. Go the other way.
Let me try for you.
Go behind Safeway.
That's what I always do.
So not, you can't turn left into the Safeway parking lot right now.
So go around to like the.
So go behind it.
This gas station.
Yeah.
Okay, I can do that.
Yeah. And Sedelis and Dragonfly are right
This
there.
entrance open, this gas station. Yes, so come, this is on this coast, come this
Yeah.
way. Okay. I can do that. That's like had another entrance there. Yeah. See, I did not know this when I picked up Safeway yesterday. Oh, and half of the pod's closed. It's a cluster.
Yeah.
think that's what it is. What is CHM? I think it's like a teenager. Oh, look, he gave me a periodic table. Yes, has it.
I found your periodic table. Welcome. So it appears we might be moving.
What?
There's a class that's over cap, that doesn't have enough room for their students in the classroom they're in. But I don't wanna just straight up switch classrooms with them because it's been one of the classrooms upstairs that actually, if it's the English classroom upstairs, it might have a similar setup. So that might work. But stay tuned, I'll let you know, but next Tuesday will likely not be here.
Okay.
And I'll let you know where it is, I figured that out.
Those are diatomics, which is this. Did we need to know this?
At some point you did.
But not now.
It'll make sense actually when we talk about this next subject, because it's all the non-metals. Because non-metals will form covalent bonds with themselves in order to fill their valences.
So are those ones that are monovalent?
Yes, the ones that are monovalent form diatomics, and even some of the others, O2 and N2. Are both, they're diatomic. But that's because oxygen will double bond with itself, and nitrogen will triple bond with itself. Turns out sulfur and phosphorus and even arsenic and selenium will also form bonds with each other, and carbon for that matter. Will form bonds with itself, but not diatomic bonds.
Okay.
So they still form covalent bonds, but in the case of sulfur, you get something. You're gonna get S8 and S8 and S12. Basically, you get these really complicated looking structures where sulfur winds up making these like ring structures, but in 3 dimensions, and then they draw it that way.
He said now it's like garage can Gauss. Oh no.
The grouse.
Yeah, it's a garage can for this.
Okay, we figured it out. So basically, all the non-metals will form covalent bonds with themselves. Some of them just do it in a more complicated way, like carbon makes diamonds or graphite.
Right.
So they're not diatomic, but they still make covalent bonds with themselves. I should just look it up instead of trying to draw it because it's not easy to draw.
I had Carl in class, and so we looked up a really complex molecule and tried to draw on the board, and it looked absolutely atrocious. Then he came in and we were like, can you guess what that is?
You'll get better at it. Organic solids.
Did you guess it correctly? Oh no, it was horrible.
No, it's not gonna be in here. Hang on.
You still don't computer.
MolView works best. So there's S8. So instead of being diatomic, sulfur makes this S8 ring structure. And then there's an S12 ring structure as well under different conditions. There you can get sulfur as an S6. Basically, you wind up with all these other strains. So the diatomics are the simplest ones. That's why we don't have you memorize what sulfur looks like. But carbon does the same thing. It has two different solid forms in its pure state, and so does phosphorus. Phosphorus has white phosphorus, black phosphorus, red phosphorus, and violet phosphorus, I think. So, and those are all pure phosphorus, but in different crystal structures. So anyway, if we're talking about, let's go back to talking about orbitals so we can talk about rotations more, and I'll make some of the rules with rotations make more sense. So Linus Pauling, famous lover of cats, and California. He's the one who theorized. He also wrote one of the most important textbooks for general chemistry of the 20th century. It was basically used everywhere until like in the 1960s. He basically was one who came up with the idea of what makes a sigma bond or a covalent bond. So they had some idea that bonds formed in order to share electrons, and he's the one who actually put some math to it. And he basically said that if you had two hydrogen atoms that each had one electron in their orbital, or in their 1s orbital, in order for them to both fill each other's orbitals, there's going to be some sort of attractive force between them. Basically, as you get the two hydrogens closer and closer together, you start moving downhill in energy. And without getting too much in calculus side of things, basically you can think of the force or the acceleration of these two being drawn together as the slope of the line. If you take the derivative of the energy, you can actually turn that into what are the forces on the individual atoms. So as long as you have a negative slope, it means you're going to keep drawing these two things closer together. And so as you bring these two hydrogens closer and closer together, there comes a certain point where you get a bunch of overlap of their two s orbitals, of the two 1s orbitals, because we're in the first energy level. And when you get to that, to a certain point, you kind of optimize how well the electrons can be in both valences at the same time. And that's basically what happens when you get to the bottom of this function here. When you get to the bottom of this function, they kind of stop accelerating towards each other. They reach sort of an equilibrium distance from each other that we call a bond length. It seems like they could get better orbital overlap though, if they kept getting closer and closer together. So how come we don't see something like this? Why does it stop at, in the case of hydrogen, I think it's like 0.74 angstroms, 0.074 nanometers. Why does it stop there? What would happen? Well, so this is the bond though. So they are bonded together. So when you say the hydrogens would bond together, what do you mean? What do we know about nuclei? They're positive. And positive charges are going to repel other positive charges, right? So basically we reach this point because if we get them any closer, then the nuclei get too close together and they push each other apart. So we're sort of balancing two different things happening, right? We have an attractive force of having these orbitals overlap so that we can fill both valences at the same time. But then we have a repulsive force of these nuclei pushing each other away. And I think where you may have been going, maybe this is where your head went. If you get these two nuclei too close together, well, one, they start pushing each other apart. But this isn't an asymptote here, because at some point they get close enough together. If the nuclei touch, then we actually get a fusion reaction happening, and then we make helium instead of hydrogen. So, but like I said, we're going to ignore nuclear forces for this class. So all that really matters is, as we're bringing these atoms closer together, there's some theoretical most stable state where the repulsion balances out the attraction.
So we won't make helium in class.
We won't make helium in class. Be a good way to win a Nobel Prize though. Right, and so Pauling further kind of took this idea a little bit further by saying, okay, well, if we know what the shape of the orbitals looks like, then we can actually treat this state as basically constructive interference between two waves, because we treat these orbitals are, they're called the wave function. Mathematically they look a lot like wave. Even though they're in three-dimensional space and we have a trouble as humans visualizing what a wave in 3 dimensions looks like, the math is there to support it. And so if you take these two functions, for example, so if this is water, the p orbital of the oxygen can be in the same phase, the same color as the hydrogen. And when you bring them closer together, you basically get the green parts overlapping with each other. And it's like when two waves hit each other, it doubles the height of the wave, right? And so that constructive interference where this orbital and this orbital are overlapping is actually what makes the bond. Because that's what allows the electron to be in both spaces at the same time. So an electron that happens to be right there is in the oxygen p orbital, and it's also in the hydrogen s orbital at the same time. And when you add those two functions together, you get something that looks like this. So that's what we call a sigma bond. Greek letter sigma, we use the lowercase. Capital sigma is the one that looks like this, that we use for addition. Lowercase sigma looks like this. And that sigma bond is really, it's not a p orbital or an s orbital anymore. It's sort of like if you average the two of them out. Right? And that's even what you do. If you have a function that looks like this, if you remember back to your math classes where you could say, okay, well, let's say we have some function f. We can make f be a sum of two other functions. We could say it's g of x plus h of x.
Yeah.
Right? We need them to add up to a total of 1, so we basically do what's called normalizing, which is basically multiply both of these by a coefficient so that they add up to 1 total. So it might be more like 0.5 g of x plus 0.5 h of x. When you put them together, you get one new function that looks like it's both of these others simultaneously. That's what's happening when we make bonds. We're mixing together these different functions. If either of you had linear algebra, second year linear algebra, not like high school algebra. Yeah. So this is what's called a linear combination of two other functions. And if both of these other functions are orbitals, then that makes what's called a linear combination of atomic orbitals, or LCAL. That's not going to come in, that's not going to be that important to, again, I guess that I'm not going to test you on what that term is, but just this concept of taking these different functions that each represent an orbital and mixing them together. That's kind of the key for how organic or how bonds form in general and what they look like.
I would mention something similar, like when you have like your original equation and you have like an equation for g of x and h of x, and then you like redo h so that it's g, like.
Yeah, there's a lot of things, there's a lot of math steps that you learn. You don't really learn applications for it though right away, right?
What I'm saying in physics. But
Oh,
then
okay, could have been.
then you could put in like the big formula and like, let's say, I don't know, g of x is like whatever formula plus and you've reworked h of x so that the variable in that formula is g,
Yeah,
and then you do it the other
Yeah.
way.
so there's a lot of different ways you can represent this. And basically, so calculating what these look like involves basically having a computer do a lot of that combination of terms and reworking of terms to try and minimize energy. Because if we're trying to figure out where this point is, we need a function that describes the energy based on where the orbitals are, right? And so basically it's these weights, these 0.5s might not actually be 0.5. What computers will do is they'll basically test this. We actually have functions for g of x and h of x. If g of x is the p orbital and h of x is the function that gives us the s orbital, we can mix them together in whatever ratio we want as long as these numbers add up to 1. And some of those mixtures are going to be lower in energy than others. And so the reason that this happens, reason covalent bonds even happen at all, is basically because it's more stable to fill both valences than to have two incomplete valences. Right, and so all of this is pretty abstract, and it's not like the atoms are out there measuring energy to figure out what the optimum bond like this. This all happens. This is our way of using human math to approximate what happens in nature. Does the orbital that act between an oxygen and a hydrogen, does it actually look like that? Pretty close. Is it still a mixture of two separate functions? No, it's sort of its own thing now. We can approximate what that energy and what that shape looks like by mixing together these other two things because it kind of does something similar, but it really is sort of an abstraction. It's just a way that we have of approximating this. So the concept that I really want you to take away from this is just the idea that as soon as you make bonds, you don't have atomic orbitals anymore. You have molecular orbitals. And your molecular orbitals look like you mix together atomic orbitals. And they're approximated. It's the sort of thing that chemists and physicists like to get into, debates on the internet about. Does this actually happen or is it not? Because it's a little bit, if you think about like Newton's laws of gravitation, do those laws actually exist or are they just humanity's way of approximating the way things move? Does the universe actually follow Newton's law? Like probably not, but it's a way we have of using math. But then it becomes semantics at some point, right? It's close enough to what actually happens in nature that we can say this happens. Even though technically it's not a real.
Yeah.
All right, one more concept. If you can have two waves hit each other and double their size, what happens when the trough of one wave hits the peak of another wave? So if we have trough trough right there. If we have the green wave out of phase with the red wave. So when the red wave is at a trough, the green's at a peak and vice versa. What happens when you add those up? Cancel each other out, right? So that's what we call destructive interference. So constructive interference is when they're in phase.
Which would be the one before.
So constructive is this version. Green overlaps with green. We're using color because we can't use positives and negatives in this case because that would imply maybe charge or up and down. We can't even use up and down because these are three-dimensional, right? So we're using color sort of as a fourth dimension in this case that we don't have a spatial way of understanding. this is what waves in one dimension look like running into each other. Then they would cancel out. In 3 dimension, when two waves of opposite phase run into each other, you get destructive interference where they both get a little bit smaller. And if you look in particular at this area right here, where you would expect to find the highest electron density for a bond, has 0 electron density if they're out of phase. And again, we're going to come back to this, but as long as we're talking about orbitals, we might as well talk about this. That's what's called an anti-bonding orbital. So bonding orbitals when you get constructive interference. Anti-bonding is when they're out of phase with each other and they cancel out. And anytime you can make it a bonding orbital, there's a way to basically flip the sign on it and get an anti-bonding orbital. The anti-bonding orbitals are going to be higher in energy than if you just kept them separate in the first place. So what this looks like, let's look at a simple example. Bromine is diatomic, as we were just talking about.
Yes.
When you bring two bromines together, they're going to naturally form a lower energy state. So the X or the Y-axis here is energy. When you bring them together, there's a way to bring them together so that they're in phase. They form a bond. And then you can put 2 electrons in that bond, and you get a sigma bond between the 2 bromines. But every time there's a way to put them together in phase, there's a way to put them together out of phase. And it's going to be, if it's a symmetrical bond, if they're both bromines, if they're both the same atom, then it's going to be just as stable as your bond is. Your anti-bonding orbital is the same amount of unstable. So it's a symmetrical potential, is the way we describe it. Why does that matter? Well, because if so, this is going to be our anti-bonding orbital. Call that we'll just put an asterisk. It's a sigma star orbital or a sigma anti-bonding orbital. This matters because if you can take an electron and promote it to the anti-bonding orbital, you basically just undid the entire bond and the whole thing falls apart. This is why some molecules absorb light and become unstable when they do. You ever notice that when you buy iodine, it's in an opaque bottle, right? Because it will match its anti-bonding orbital is low enough in energy that visible light will cause it to split, become two iodine atoms. It gets really unstable. And hydrogen peroxide will do the same thing. Right? So anything that's sold in an opaque bottle, that's usually because it's light sensitive. Light degrades it. Usually that's because light, visible light or near UV, has enough energy to promote electrons up to that anti-bonding orbital.
So that means you would end up with water in most cases?
You wind up with in the case of peroxide in particular, you get peroxide radicals, which then react with other things to make hydrogen gas and oxygen gas, which is why one of the reasons why they don't sell hydrogen peroxide at high concentrations is because when it gets old, it gets explosive.
Oh.
All right. Here's the final topic, big takeaway from the day today, or from the second half. Pauling realized that just that idea of half-filled orbitals overlapping doesn't explain carbon. Because they knew that carbon made stable compounds when it had 4 bonds. But if you look at the molecular or the atomic orbitals for carbon, it only has 2 half-filled bonds or 2 half-filled orbitals. So regular, what they call valence bond theory, would predict that we only would make 2 bonds with carbon, and we knew that wasn't true. So what Linus Pauling won his first Nobel Prize for was by basically saying, okay, well, what if we take that same approach of mixing together orbitals and apply it to the atomic orbitals? If we took the 2s and we mixed it together with the 2p orbitals, then we could actually get 4 orbitals that were the same energy. They're going to be somewhere in between. So again, this is energy on the y-axis. By mixing together the 2p and the 2s, we get 4 orbitals that all have the same energy, and now we can put 1 electron into each of them. And now it can make 4 bonds. So the reason that this happens is because just leaving it like this, yeah, the 2s is more stable this way, but you can't fill the atomic orbitals. You can't fill the valence shell without mixing them together. And so that process is called hybridization. You did learn this, but it's been a while.
Yeah.
And it probably didn't make much sense at the time.
Not a whole lot did in that class, I'll be honest with you. Until I got to the OChem section, and then I loved it, but the math part I could not do.
That's fair. This is not easy math to do. But basically, and again, I'm going to hand wave the math. We're not actually going to calculate this because you actually can't calculate this math by hand. You wind up with the fact that you have all these, anytime you get to a system that's more complicated than 1 electron around the nucleus, we actually don't have the math as a species to be able to solve that. It's an insolvable problem currently. We can approximate it. What we do is basically just do glorified guess and check. You start with a guess and then you tweak some of the numbers and see if the energy comes out lower. And then you keep tweaking it until you get the same energy twice in a row. Say, well, that's probably pretty close to the real answer. So don't worry about doing the math for this. Even when I was in grad school, the most complicated it gets. Taylor, are you done with the physics sequence here yet?
Yeah.
You take university physics or trig physics?
Trig.
So you probably didn't have to do a particle in a box. Basically doing the math for this with 1 electron in a confined space. And you can actually generate the function that looks like a 2-dimensional s orbital.
She's also doing trig-based.
Yes.
Yeah, I just started.
You just started it. So when you start talking about quantum in university physics, you actually have to do the math once. And it'll take about a page to do 1 problem. And it's all calculus based, and it's all calculus and sine wave space. So it's beyond what you need to do.
All right.
And we can't even solve it analytically as soon as you get to 2 electrons anyway.
Right.
So what we do is we approximate it, and then we just, in this class, we're basically going to just use the concept of mixing these orbitals together.
Okay.
All right, so that's right. This is going to be a common theme in chemistry. Every time you learn something, the hybridization you learned in Gen Chem, we're now going to learn is not quite accurate.
Yeah.
And we're going to add another layer. It's not that it was wrong. It's not oversimplified and useless necessarily. But it's also not the full picture.
For every lecture. Yes, I taught it the super way, but actually that's wrong and it's this.
Yeah, and it is one of the reasons why older researchers fight progress in some cases. There's a saying in the sciences that there's new ideas are never truly adopted. It's just that the old instructors die. And then the ones that grew up with it being normal. So you're seeing it in a very accelerated. This was 150 years of research crammed into 1 lecture.
Right.
So that's why it feels like that. It is like that. They thought this, and then we realized it's more like this, and then we realized it's more like that. All right, so the way that this works, like I said, is you basically are just going to take these functions, mix them together to make 4 new orbitals that are a combination of an s and a p orbital. But remember that the p orbital has 3 pieces. It can hold a total of 6 electrons. And so that's actually technically 3 separate functions that all have the same energy, just with a different orientation. Remember we talked about that on Tuesday? The x versus the y versus the z. They're the same function oriented perpendicular to each other.
Yeah.
So we actually get to mix 3 pieces of the p orbital, and you get to mix all 3 functions together. And when you mix all 3 functions together, you get 4 new functions. So all 3 functions plus an s orbital. There are 4 different ways you can arrange it now.
But you get rid of one of your s.
So the s orbital becomes part of these. So we took 3 plus 1, and we still have 3 plus 1. It's just now they all look symmetrical.
Yeah.
They're all the same energy.
So,
They're not going perpendicular to each other anymore. Now they're 109.5 degrees from each other. So this is actually where the tetrahedral structure comes from. Yeah. If you take these functions plus an s orbital and you mix them together, you put you mix up your positives and negatives, say +1 here, -1 there, +1 there, +1 there, and you mix them all together, you get orbitals that are tetrahedral relative to each other. And so we call those orbitals, we call them sp3 orbitals, because they don't look like s orbitals anymore, but they also don't look like p orbitals anymore. And so that's actually what we see participating in these sigma bonds. It's not the atomic orbitals. So here we treated it like it was the oxygen's 2p orbital that was overlapping with s orbital. That's not actually accurate either. Because really it wouldn't look like a p orbital, it would look like an sp3 orbital. And an sp3 orbital basically it's going to look like it's kind of like a skewed figure 8 where the bottom is out of phase with the top. And these will naturally align themselves to be at 109.5 degrees.
I'm confused now.
So this is if you took all your sp3 orbitals and you attach them to the same thing. So these sp3 orbitals, they kind of, like I said, they look like a big skewed figure 8. The other way you can think about it is think about like a regular balloon shape. Where this point right here, that's the knot.
Yeah.
And then you get the little bit that hangs off the nozzle of the balloon that's still left over, right? So if you blew up 4 balloons and held all 4 of them by the knot, they would naturally arrange themselves to be in a tetrahedral shape. So this is a messy drawing, partly because it's really hard to draw in something that's 3-dimensional and abstract in 2 dimensions. But picture holding 4 balloons by the knot. And they're naturally going to shape themselves to be sort of this.
And they're sort of.
Kind of like a clover, yeah. And the points of those, the ends, are going to look like a 3-sided pyramid. Right, so the balloon knot is right in the middle of that 3-sided pyramid now. That shape, that 3-sided shape, that's a tetrahedron. So a tetrahedral geometry just means that your central atom is sitting right there. It's got 1 bond going straight up, 1 off to the side, 1 back into the board, and 1 coming forward. Right? And the reason that it takes that shape is because that's the way you can mix together 3 p orbitals and 1 s orbital and keep them all as far apart as possible and the lowest possible energy. So this is why the tetrahedral shape, remember how I told you weren't gonna really need to memorize the names for all the geometries again? Because we're just gonna talk about them in terms of hybridization for this class mostly. We'll use terms like tetrahedral and linear and things, say
Which ones should we, just to, like to.
tetrahedral and down. But just as often, I'm just gonna say that carbon is sp3.
And is that for? That is the, with the lone pair, yeah, which one do we have to memorize?
So
Or just
tetrahedral, just know that what the shape of a tetrahedral molecule is, because it doesn't really matter if one of these points is a lone pair, right?
Right,
It's still sp3 and it's still the same general bond angles. And so what if we're not gonna make, so the whole reason that we did that this happened was so that we could make 4 sigma bonds. What if we're not gonna make 4 sigma bonds though?
go back to two.
Well, we're still gonna wanna make, if we're, as long as we're making 3 bonds, we're still gonna wanna hybridize these together a little bit, right? We're just not gonna take all 3 pieces of the p orbital.
That's an option, just taking part of it.
It leaves the other part of the p orbital called unhybridized. So what happens is if you take 2 parts p and 1 part s, you get an sp2 orbitals. And then you're left with an unhybridized p orbital.
Okay.
Why would that be an advantage? If you're trying to make pi bonds. Pi bonds are what you get when you make a double bond. So because if you can't really have a double bond in between, let's just say we're talking about 2 carbons here. If you had an sp3 orbital overlapping with another sp3 orbital, this is when it gets really complicated. So overlapping those, that's gonna make a sigma bond, right? Kind of like what we talked about, they're gonna overlap, you're gonna create some constructive interference between the 2 carbons. If we're trying to make a double bond between these 2, where is it gonna go? Because it can't go on top of those because you can't put electrons in the same physical space. You can only put a total of 2 electrons in the same physical space. So if you're trying to make a double bond, the other bond, the second part of the bond, is going to be mixing together p orbitals. P orbital on this carbon with the p orbital on that carbon are going to get mixed together. Just like we mix together 2 orbitals to make our sigma bond here, we're going to mix together 2 p orbitals to make a pi bond. So basically, it kind of looks, if you have a better rendition of it, it can look like either like 2 long balloons, one on top and one on bottom with opposite phases. Sometimes they get drawn kind of like an upside down canoe. Yeah.
I've seen who can read them.
So this is what the unhybridized p orbitals look like. And then they kind of like smear out when you average them together, when you mix the 2 functions together. I don't have one that actually looks the way I was thinking. But you get something that looks like that. But in order to make that pi bond, we can't have that p orbital hybridized. So basically, the double bonds are less stable than single bonds because you have to have this unhybridized p orbital. And so that means what's left over is less hybridized. So when you made a tetrahedral structure, it was sp3. So we mixed together 4 things to make 4 electron groups taking up space. As soon as we add a pi bond in there, we only have 3 things taking up space now, right? Go to one example of a molecule with pi bonds. So this is formaldehyde. this carbon in the middle has 4 bonds, so it's stable. But the bond in between the oxygen and the carbon is a sigma bond and then a pi bond. And they're both in the same physical space. Which means you only have 3 electron groups. This is the why behind why, when we were talking about electron geometries, we said, oh, well, a double bond only counts as 1 electron group because they're all in the same space. And that means that this carbon only has 3 hybridized orbitals. So instead of being sp2, it's instead of being sp3, it's sp2. Versus if we had methanol, we have 4 things taking up space. So you need 4 hybridized orbitals. So it's not sp2, this carbon is sp3. So basically, sp2, sp3, all the hybridization is like a direct 1-to-1 translation with electron geometry. If it's tetrahedral, it's sp3. If it's trigonal planar, it's sp2. And if you only have 2 things around that central atom, it's linear, right? So how many orbitals do we need to mix together for that one? We have to have 2 pieces on this middle carbon. This middle carbon's going to have 2 p orbitals that are unhybridized because it's got a double bond to the left and it's got a double bond to the right. So we don't have, and we remind you what the orbitals look like. We got sp3 by mixing all of them together. We got sp2 by mixing together these, but leaving the other one unhybridized to make a pi bond.
So hybridization one.
So we're going to hybridize one of them. We are just going to get sp. And then the other 2 pieces of the p orbital are available in a pi bond, which is what this is showing. So this is acetylene, which is carbon triple bonded to another carbon. The same acetylene they use for welding. These 2 carbons have 2 pi bonds and a sigma bond. The sigma bond is hybridized. The pi bonds are not. So the hybridization on these is just sp. So basically, your quiz this weekend is just, here's the molecule, what's the hybridization of all the heavy atoms? The heavy atoms mean everything bigger than a hydrogen. And all you have to do is count how many electron groups are taking up space. And you mix that many orbitals together. You always start with an s, and then you add as many p orbitals as you need. So, for instance, if we had NH3, it's tetrahedral in shape. So it's got that lone pair taking up space. What is the hybridization going to be? How many electron groups are around the nitrogen?
Wait, does the lone pair count?
Does the lone pair take up space? So it counts. So it's sp3.
But double and triple bonds just count as one.
Double and triple bonds just count as 1 electron group because for every double or triple bond you have, that means that you have to have some unhybridized p orbitals in order to make it look like this.
And the SP, SP2, SP3 will need applies to the central.
So we're going to get away from the idea of the central atom because they're all central atoms can change our frame of reference, right? So like for this molecule, what's the central atom? Carbon.
Well, when we just look at the longest carbon chains.
That's how you would name it. But basically every carbon, every atom that's heavier than hydrogen will have its own hybridization. So when I say what is the hybridization, it's of each carbon atom. And so we'll do this one, I know we're out of time, but if we do this one, I think it'll help you on the quiz.
Yeah.
How many electron groups around that carbon? Give us just a couple seconds. 4, so it doesn't matter what the rest of this molecule is, you're just looking at that carbon.
Yeah.
So 4 electron groups means what hybridization? sp3. Any other sp3s we can identify right off the bat?
The carbon next to it. I mean, wouldn't all the carbons be sp3s, because they're always gonna. Yeah.
All the carbons,
Cause we don't count doubles and triples in this.
double and triple bonds, the pi bonds don't count for hybridization.
So then the other one that's, that one.
So all the purple ones are sp3. How about these middle two?
SP2.
They're both gonna be sp2. This carbon has 2 pi bonds, so it's sp.
If you were to put like SP1, would it?
No,
Okay.
that's one of those ones where it's like somebody who doesn't speak English as a first language. Sometimes they say things that aren't technically incorrect, but you're like, oh, you're not as used to this as I am, sort of. So it's one of those where if you said SP1 to a chemist, they'd look at you funny, but they wouldn't say you're wrong.
Right, okay.
Alright, so that's,
The exam is, your quiz is just complete like this, like identify.
here's a molecule,
Okay.
write out the hybridization for everything.
It's like the 3D shape once they're hybridized, that's where I mean.
We'll spend more time with that next week.
Okay.
For now, I just want,
Like,
I want you to be really
when I
conversant
see
with
it,
this.
but it's
Yeah.
pretty. They all start the same, as they're all in the same color and then
Yes, we'll try and get better about that, but it's one of those things that takes a little bit of practice. And we'll get better with it, but we're gonna use these terms really quickly to say, oh, the sp2 carbon is gonna do this, or the sp carbon has this property. So it's gonna be like a shorthand, so that we don't have to say trigonal planar all the